So in this problem, we're going to look at buffers in the simple common ion effect. So we have nitrous acid, which is HNO2. On the handout you received, there might have been a 3 there, but it should be HNO2. Nitric acid is a strong acid, so it would not have a Ka value. So we have nitrous acid and potassium nitrite in solution. So we have common ions. There are really two ways to deal with this equation. The first is the ice box. So let's have a look at what that's going to look like. Try and make my ice box nice and neat. So we have 0.085. We have none and none. 0.10 molar potassium nitrate, and that's coming from there. So if you have a weak acid, salts or soluble ionic compounds of the conjugate base will be strong electrolyte. So if you have a weak electrolyte producing a conjugate pair, the salt of that conjugate pair will be strong. So if I have zero point 0.1 moles of the strong electrolyte, that means I just have 0.1 moles of nitrate now in solution. So minus x and plus x, and we know whatever side has the 0 is going to be gaining x. So we can check to see if we're able to ignore x. In this case, we'd have to do it for two different situations. So 0.085 divided by the equilibrium constant. And I have 188, so I've got to include x here. And 0.1 divided by 4.5, 4 negative, is 222. So x is going to have to be included here. Now, we know that the Ka is equal to the concentration of H plus there's our Ka expression. So we're going to substitute in what we need. 4.5 times 10 to the negative 4 equals x times 0.1 plus x all over 0.085 minus x. So we start multiplying this out. 3.8 times 10 to the negative 5 minus 4.5 times 10 to the negative 4x equals 0.1x plus x squared. Let's get this into quadratic form. So now we use the quadratic formula to solve. And we get that x is equal to 3.79 times 10 to the negative 4, which would be the only reasonable root that was produced. And this is equal to the concentration of H plus. pH is equal to the negative log of the concentration of H plus, which is equal to 3.42. So take this number, take the negative log of it, and you should get 3.42. The second way to do this would be to try and use the Henderson-Hasselbalch equation. It would be a great approximation method, but the issue, of course, being is that in this particular case, we are not allowed to ignore x. So it might be interesting just to see what that answer would be. Base over acid. So pH is equal to the pKa. Remember what the pKa is. The pKa is the negative log of the Ka. So 4.5 exponent 4 negative is equal to 3.35 plus the log of the base is 0.1 over the log of the acid, 0.1. So 0.1 divided by 0.085 log plus 3.35 is 3.42. So in this particular case, it looks like it's actually going to be an okay approximation. It is a little risky to use because we know that we're not going to be able to lose x, but from class we've talked about how you're talking about 10 to the negative 3 usually when Henderson-Hasselbalch is not useful, but in this case we seem to be okay. So the answer is definitely 3.42, and we've confirmed that in two different ways. So for question 2, we're looking at the another equilibrium, but basically we have a common ion present. And in this case, we're looking for both pH and the formate ion. So we have formic acid, HCOOH, going into H plus and HCOO minus. Initial change in equilibrium. Let's draw our icebox out. Now we're looking for the formate ion, so we're going to have to go to the icebox anyway in this case. But we just saw how we could use Henderson-Hasselbalch in certain situations. And in this situation, if it was just looking for the pH, we would not really have much of a problem. We know that the concentration of H plus is equal to pH. And in this case, the pH and the formate ion should have the same concentration. So we could take the Henderson-Hasselbalch approach, but we're just going to use the icebox here. 0.05000 minus x plus x. Oh, this is 0.1, sorry. And 0. 0.05 minus x, 0.1 plus x. This is plus x. So Ka is equal to the concentration of H plus, concentration of HCO minus, the concentration of HCOOH. We substitute in our lines. So 1.8 times 10 to the negative 4 is equal to 0.1 plus x over 0.050 minus x. So we now should be getting pretty good at turning this into quadratic formula. So 0 equals x squared plus 0.1x minus 9 times 10 to the negative 6. So we have ABC, so we can use our quadratic formula and solve x to 8.99 times 10 to the negative 5 moles per liter, which is equal to the concentration of the additional H plus, and it's also equal to the concentration of the formate ion. So if I have 0.1 and I'm adding 10 to the negative 5, then realistically I probably could have ignored that. So the pH is equal to the negative log of the concentration of H plus. The pH in this case is equal to the negative log of 0.1. And the pH is equal to 1.0. The concentration of the formate ion is equal to 8.99 times 10 to the negative 5. There's our answer. So in this problem, we're looking at determining the pH of a buffer, and then we have benzoic acid and sodium benzoate. So essentially, we can simplify this to make the acid HA and the benzoate A minus. So we end up with HA dissociating into H plus A minus. So we have the acid, and A minus is the conjugate base. So this is the concentration of the base, and this is the concentration of the acid. So we're going to go right after Henderson-Hasselbalch. So the pKa in this case is the negative log of 6.3 times 10 to the negative 5, and that equals 4.2, plus the log of the concentration of the base, 0.2, over the acid, 0.12. The pH will be equal to 4.2 plus 0.2. The pH will be equal to 4.4. That's all we do to solve a buffer. So for question 4, we have essentially a little more work to do. It says a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution. The pH of the buffer is 4.74. Calculate this pH after 0.02 moles of NaOH is added. So this is going to look very similar. It's going to look very familiar, how we're going to approach this, but it's actually not going to use an ice box. We're going to use a before, change, and after box. So when you add NaOH, you are adding a base. There's hydroxide in it. So that means it's going to deal with the acidic part of the buffer. Now you have two species to choose from. You have acetic acid and sodium acetate. So obviously acetic acid is going to be the acid. So because I have a base, I'm going to pick the acid that's going to react with. So CH3COOH plus OH negative. Sodium is irrelevant, it's a spectator. And that's going to pick up the H here, leaving me with acetate plus water. So in this particular solution, we go before and after. And some people will use before added after. Let's throw in an added here. Before added after. So before I had 0.30 moles of this. I had 0.0 before I added anything. Make sure I know what I'm doing. And I had 0.300 moles of this. And the amount of water is just irrelevant here in all three lines. Now, I didn't add any of this. I did add 0.02 moles of the hydroxide. Now, this is where stoichiometry comes in. If I add 0.2 moles of this reactant, it's going to completely react. And it's going to form 0.02 moles of the acetate. Again, some water as well, but it's irrelevant. Now, that means I'm going to have to react with some of this. So I'm losing some acid to react with this. So I've added this. It's going to cause this to react and it's going to disappear. After this reaction, I'm going to end up with 0.280. This will be reacted, and 0.32, and the water doesn't matter. So as we look at this situation, what we have is basically just looking at the stoichiometry. This is not an equilibrium, this is a one-way arrow. So basically you add some reactant, it reacts with it and decreases the concentration of acid, but increases the concentration of your base. So now that we have our new acid and our new base, we can go to Henderson-Hasselbalch. The pKa of this system is 4.74. Plus the log of 0.32, 0.28. The pH is now 4.80. And that makes sense because we've added a base. The pH was 4.74, meaning the pH has increased. And one of the things that's really helpful here is if you recognize that the amount of acid and base is equal, when that is true, when the acid and base are equal, the pH is equal to the pKa. So without even looking up the Ka for acetic acid, we knew what the pKa was. For comparison's sake, we're going to figure out what the pH of a solution where 0.02 moles of NaOH were added to water. So basically, NaOH goes to Na plus OH negative. And we end up with 0.02 moles of NaOH. POH is equal to the negative log of the concentration of OH. POH is equal to the negative log of 0.02. POH is equal to 1.69. pH is equal to 14 minus POH. pH is equal to 12.3. So it's a really nice way to look at the comparison between adding the same amount of base in both situations. First, dealing with an acid, dealing with the acid part of a buffer, and second of all, when you were just adding it to pure water.